Swayam Prabha. Digital India. Educated India.
Welcome to lecture 7 of flow of water through soils. In the previous lecture, we have introduced the flow net concept and then we constructed methodology for predicting the rate of seepage through isotropic materials. In this lecture, let us look into how we can solve some problems by using the concepts which we have discussed in the previous lecture. Then we extend our knowledge for calculating the rate of seepage through anisotropic material, being anisotropic in the sense from the permeability point of view, having different permeabilities in horizontal and vertical direction. Thereafter, we will look into how we can calculate the rate of seepage through an earthen dams. So let us look into this particular concept once again, the flow net method of construction. So here, for determining the seepage, the flow net solution, the computation of the rate of seepage, we discussed that it is formed by the two orthogonal two families of curves. One is formed by equipotential lines and flow lines. The space between any two flow lines we call as flow channel, and the head difference between any two equipotential lines we call as potential drop. So based on this, equipotential drops between two flow lines is delta H is equal to HL by ND, HL by ND. ND is the number of the potential drops. So from the Darcy's law, if you again apply, then we said that Q is equal to K into HL. HL is the total head loss which is occurring, NF by ND, that is number of flow channels to number of this potential drops to A into B is nothing but the aspect ratio. So we said that while constructing the curvilinear squares, this aspect ratio is be maintained as 1. So let us look into a problem. So flow net around a horizontal drain. Let us consider in this particular slide what you are seeing, a drain which is found at 3 meter from the top surface, which is placed in sand, having coefficient of permeability 5 into 10 to the power of minus 7 meter per second, isotropic in nature, and the center of the this drain is 3 meters from the top surface. The water table is found to be at the top surface itself. The free water surface is found to match with the top surface of the soil. So the depth of the soil which is under consideration is around 6 meters. So this is the long horizontal drain. So here what we are considering in this problem is a long horizontal drain. So this particular aspect also can be now studied as a two-dimensional problem. So in this case now, if this is the x direction, this is the z direction, then this again turns out to be a two-dimensional problem. Now consider this top surface of the soil or top surface of the water as datum. Now by using this flow net concept, if you look into it, we can draw flow nets. Keeping in view of the symmetry, the central line, you can see here the stream of equipotential lines and flow lines. So the flow takes place like this in this direction, because the head loss occurs in this direction. So the flow occurs in this direction, and then this drain tries to divert the water from this. So we are interested in finding out the rate of seepage, and then this particular pore water pressure at this particular location x here, which is shown in this slide, and also the velocity of the flow. So this 3 meter is the center and this is the flow net and this is the symmetry. So, you have got two symmetrical mirror image type flow nets which are shown here. So, here what you are seeing, this is the first equipotential line, second, third, 4, 5, 6, 7, 8, 9. So, by the time here if it comes, the head which is there for the flow to take place is around 3 meters. So, when the flow which is actually commencing from here, so it is in the flow is this direction. So, as per our conventional numbering, we numbered like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Similarly, this side. Then flow channels. So, this is the first flow channel, second flow channel, third, 4, 5, 6. So, these are the number of the flow channels which are determining this particular flow. So, this is in this slide what we are trying to do is that rate of flow net construction, for example, a long horizontal drain, and that is can be considered as a two-dimensional problem. So, let us look into the solution. So, flow net around the horizontal drain, that is the example under consideration for us. Find the discharge to the drain in meter cube per day per meter length of the drain. So, per meter length of the drain, so suppose if the drain is of 100 meters, then it can be, we can calculate by using this concept. So, considering the datum at the free water surface, so this makes the total head at the top of the ground is 3 meters. With that, the total head at the top of the ground is around 3 meters. So, HL, that is head loss from the surface to the drain, it is around 3 meters. So, by considering only one half of the flow region, so keeping in view of the symmetry, consider only one half of the flow region. If you count, then number of flow channels are 6, number of potential drops are 9. And being isotropic in nature, we can use Q is equal to K HL into NF by ND. Being symmetrical, isotropic, being curvilinear squares, the aspect ratio A by B can be assumed as 1. So, by substituting now these values, the K is the coefficient of permeability and H is the head loss and number of flow channels, number of potential drops, and multiplied by 2 because we have the two flow regions determining this longitudinal drain. So, multiplied by 2, which gives us 0.1426 meter cube per day per meter run of the pipe. This is the rate of seepage or rate of discharge which can occur in per meter run of the pipe. So, by using this concept of flow net construction, simple problems like the drain problem which we consider and we treat it as a two-dimensional problem and it can be solved. Now, flow net around the horizontal drain and the same problem which we continue now. Find the pore water pressure at x 1.5 meter into the soil directly above the drain. That means that if you go into the previous slide, this is x which is 1.5 meter below the ground surface and directly above the center of the drain. So, there we are required to determine what is the pore water pressure. So, if you look into this, potential drop between two equipotential lines is around 3 by 9. So, N is the number of total potential drops and head loss is around 3. So, potential drop between any two equipotential lines is around 3 by 9. The total head at x, that location x which is 1.5 meter below the ground surface and above the center of the drain, that can be given by total head at 6 is equal to 5.6 by 9 into 3. So, the total head at x which is available is around 1.867. That means that it started with 3, by the time it came here that much head is already dissipated in the form of a flow which is taking place through the soil. So, elevation head at x is 1.5 meter because the datum is at the ground surface. So, elevation head is 1.5 meter. So, pressure head at x is equal to, by using total head is equal to pressure head plus plus elevation head. From there we get 0.367 meters as the pressure head at x. So, pore water pressure at x is equal to 0.367 into 10, around 36.7 kg per meter square by treating this unit weight of water as 10 kilonewton per meter cube. So that is how we can determine pore water pressure at different locations. If you know the where exactly the pore water pressure is required, and if you know from this construction, we can estimate what is the head at a particular point. From there, by looking into the elevation head, we can calculate the pore water pressure at a particular location. So this is an example which demonstrates, but by using the same concept, we can determine the pore water pressure at different locations. So estimate the velocity of the flow at x. So we are also been asked to determine velocity of flow at x, that location. So let the vertical length of the curvilinear square at x is around 0.4 meters. So let us assume when this particular flow net is drawn to a scale, we can easily get the vertical length of the curvilinear scale at location x. If that happens to be 0.4 meters, then now the hydraulic gradient is nothing but 0.33. That is because head drop between any two equipotential lines is around 3 by 9, that is 1 by 3, around 0.33. That divided by the length of the flow, that is around 0.4 meters. So with that, the hydraulic gradient is obtained around 0.83. By using now the Darcy's law, V is equal to Ki, K is known to us and I is known to us. From that we can get, see, the velocity of the flow at x is given by 4.75 into 10 to the power of minus 7 meter per second. So in this problem, what we try to do is to determine the seepage or a discharge through pipe per meter length, and then by treating that long horizontal drain has a two-dimensional problem, we constructed flow net and it has got two flow regions. So by using the concept of the method of flow net construction, the flow nets are constructed by approximating as a curvilinear squares, and then we determine the number of flow channels and number of potential drops. Then we try to obtain the seepage, and from there we try to calculate the pore water pressure at a particular location which has been asked in this particular problem as x, and then we try to calculate the velocity at a particular location x. So having discussed the flows in isotropic materials, let us try to look into the flow in anisotropic material, that is the flow nets in anisotropic material. How to deal about this? So in developing the procedure for plotting flow nets, we assumed that permeable layer is isotropic. That means that K horizontal is equal to K vertical. Being a two-dimensional, K horizontal is equal to K vertical, we assumed, which is equal to K. So that is isotropic as far as permeability is concerned. Consider the case of constructing flow nets for seepage through soils that show anisotropy with respect to permeability. So now consider the case of a constructing flow nets for seepage through soils that show anisotropy with respect to permeability is concerned. Anisotropy with respect to permeability concerned means the K horizontal is not equal to K permeability. So in that case, what we should do and how to construct the flow nets? So for two-dimensional problems, when say K horizontal if it is equal to Kx, K vertical if it is equal to Kz, then we can write from Laplacian equation as Kx is equal to dou square h by dou x square plus Kz into dou square h by dou z square is equal to 0. That is for two-dimensional problems. In case of isotropic problems, what we said is that Kx is equal to Kz is equal to K and not being equal to 0, we said that dou square h by dou x square plus dou square h by dou z square is equal to 0 is the Laplace equation for a two-dimensional problem. But in case of anisotropicity, as far as from the permeability is concerned, Kx into dou square h by dou x square plus Kz into dou square h by dou z square is equal to 0 is a Laplacian equation. Now the same equation, by rearranging the terms, we can write in the form of equation A, which is shown here as Kx by Kz into dou square h by dou x square plus dou square h by dou z square is equal to 0. A closer analysis of the above equation indicates that a simple Laplacian equation may be endangered if adequate change of variables is used. So let us try to write the same equation by substituting x is equal to, that is capital X is equal to small c times x. Capital X is equal to small c times x, where c is a constant. Now by writing this now, dou square h by dou x square plus dou square h by dou z square. So with that, by substituting for x is equal to cx, we can write the same equation dou square h by dou cx whole square plus dou square h by dou z square, which can be written as 1 by c square into dou square h by dou x square plus dou square h by dou z square is equal to 0. So let us call this as the equation of the form which is indicated by B. So now comparing the equations A and B, the constant c can be identified as now as c is equal to root over kz by kx. By comparing the equations A and B in the previous slide, we can obtain the constant c, which is identified by comparing the equations A and B as c is equal to root over kz by kx. So equation B is of the same form as dou square h by dou x square plus dou square h by dou z square is equal to 0. So which governs the flow in isotropic soils and should represent the two sets of the orthogonal curves in capital X small z plane. So the z is again same, but x is now which is different because we are now trying to convert anisotropicity into some transformed section. So here the x is equal to which is nothing but c times x. Now the c, if you substitute for root over kz by kx, we can write capital X is equal to root over kz by kx into small x. So now consider now the flow nets in anisotropic material. So if the flow through the natural anisotropic section if you take, and this look like this, which is L and then same depth d, assuming that the flow is taking place in the vertical direction along that is in the z direction or z axis. Kz is the permeability along the z axis and the flow is occurring over L into 1 meter, that is per meter length of a plane which is considered here. So in this case permeability is occurring over a flow is occurring over an area of L into 1. So assumption is that anisotropy merely causes a linear distortion of the flow net. On the assumption that anisotropy merely causes the linear distortion of the flow net, the flow through the natural anisotropic section which is shown here, d is the depth and L is the length and kx is the flow which is along the x direction, kz is in the vertical direction, that is z direction, and q is the flow amount of flow which is occurring through this. Now flow through the transformed section, if you look into it, because we have to now convert that into a permeability which is isotropic in nature. So for that, let us assume that Kt is the transformed permeability which is in both in horizontal and horizontal direction as well as in the vertical direction. So if that is the case, then the flow through the transformed section which is again converted into isotropicity, that anisotropicity is converted into isotropicity by considering a which is called a transformed permeability. So in that case, this length is now taken as L into root over kz by kx. Still to satisfy again, even with this also, with the transformation whatever we are doing, we should see that again the Laplacian equation is satisfied. So here the length is now L into root over kz by kx, and which is small, being because we have already discussed that kx is always more than kz. That is under the assumption that horizontal permeability is more than vertical permeability. Now starting with the natural section, that is on the left hand side in the previous slide, the flow quantity per unit length can be written as q is equal to L into 1, that is area over which the flow is occurring, into kz, that is the permeability, and I is the hydraulic gradient with which the flow is occurring. That is, let us write that equation as C. Within the transformed section now, the same quantity of the flow is calculated as follows, but now that L, which is now this transformed length, which is nothing but L into root over kz by kx into 1, that is the area through which the flow is occurring, with a permeability kt but same hydraulic gradient I. Now comparing C and D, with that the second with the transformed section, the same quantity of the flow is calculated, and if that is indicated as C, and comparing C and D, the transformed permeability can be obtained as now Kt is equal to root over Kx Kz. So the transformed permeability, for example, if the anisotropicity is there and if Kx is not equal to Kz or K horizontal